Nucleophilic substitution is the first type of organic reactions that you will learn about in organic chemistry. And it's based on the polar carbon-halogen bond, this bond right here. And the origin of this is that C is less electronegative than X, which is your halogen. So it gets the delta plus, and X would get the delta minus. So what that does is that it creates an electrophilic carbon, which, remember what that means is that it's electron deficient. And this is what drives the reaction. So in this case, is that this electrophilic carbon, electron deficient, will react with electron-rich reagents, or what we call Lewis bases, nucleophiles, and Brunstad-Lowry bases. So again, those electron-rich reagents are going to find their way to react with this carbon that is electron deficient. So nucleophile, electrophile. When we talk about nucleophilic substitution reactions, they usually have this form, or this general form, this general reaction. For example, if you have a methyl halide, that's, just a methyl with a halogen attached to it, or a primary alkyl halide, like the one you see right here. This is a primary alkyl halide. And you react them with sodium ethoxide, which is this right here, your electrophile, or your nucleophile. The reaction occurs in which the nucleophile replaces the halogen, which is expelled as a halide ion. So what happens here is that you have this Na is a spectator ion, so we don't even consider it. And this has these lone pairs, this oxygen. And notice what happens on the other side. That Br is out right here. And it's replaced by this right here, which is your nucleophile. This right here. So you see the substitution occurring. And again, what's driven this reaction is that you have an electrophilic carbon right here. So that's a delta plus, and Br would be the delta minus. So again, this is what happens. So what are common nucleophilic reagents? We will go in depth into this, but just to introduce you to some, here are some. You have some that are based on oxygen nucleophile. So this is an oxygen with a negative charge. Of course, it has its lone pairs on it, like hydroxide, alkoxide. This is phenoxide, meaning, it has a phenyl group or an aromatic. Sulfide, nitrogen, like ammonia here. Again, you look at the lone pairs here. Remember, that's what forms the new bond is you need electron pairs. Amine, this is azide. They have enough electrons. So of course you can form CC bonds, new CC bonds. Like here, you have a cyanide, etc. So these, all of these have one thing in common, is that again, they have lone pairs, they're electron rich. So notice the lone pairs that I'm drawing. So again, they are electron rich. And the bond, as we emphasized in the last chapter, in chapter 6, occurs again between your electrophilic carbon. Notice how the reaction took place here between the oxygen and the electrophilic carbon. So I'm going to put the delta plus so you can see it. And that's your oxygen right here. So you cannot just put them together without knowing where the attachment occurs. Remember, that's what we learned in the last chapter. So a nucleophilic substitution reaction can be used to transform alkyl halides into a variety of other functional groups. Absolutely. So how do we actually go about doing substitution reactions? Like I said, we will learn about two different mechanisms that are in competition with each other. But the general substitution reaction looks like this, is you have Z, which is your, in this case, leaving group, and Y comes in and replaces Z. So again, that's what happens. And here's an example. You have I on this methyl iodide, and look at the chlorine replacing the iodine in this case. So you see the general form. As a general rule, and we're going to go back, we're going to see this as we go through, is that you always find the sp3 hybridized carbon with the leaving group, or in this case, X, or Z, where Z is attached. So you look at this right here. Generally, we're going to use the CX here. And then you identify the nucleophile. So like in this case, we said this was X and this was the nucleophile with the lone pair or the pi bond. Mainly, of course, it has lone pairs. And then you substitute the nucleophile for the leaving group and assign charges, if necessary, to any atom that is involved in the bond breaking or bond formation. So as you saw here, Cl replaced I. And it's out. Generally, like I said, X is known as a leaving group. Lg stands for a leaving group. Here's an example. Look how I would do this. But then, of course, we would discuss more in depth there are differences in those reactions. So what I would do in this case, in this reaction, is I would, again, find my electrophilic carbon, my sp3 carbon. And that would be this right here. It's the only one. And then this would be X, or the leaving group, Lg. Let me make this a little bit clearer. Don't know if it's a little bit clearer, but it's better than nothing. So, and then look what happens. You have another lone pair that's not shown. Here it is. You're taking the OH minus, kicking the Br out, and that's going to be your new bond. So look how it would look like. You'd have CH3OH. Or, of course, you can just draw it as CH3OH. So this is an alcohol. So you went from an alkyl halide to an alcohol. The same thing here is, again, where you see that lone pair kicks the Br out, and then there's going to be your new bond. It's going to be CH3. So you made an alkyne. So notice how I made the replacement. Here's my carbon. There it is right there. So very important that you attach it at the right place. Otherwise, it's not correct. Of course, you have the Br out. We're not including it, but we're just going to show it right here. Here's Br minus, and of course, here's also Br minus. So, but you might say, okay, well, it's very easy. I just go where my lone pairs are and just replace it. Well, if you do this reaction, you actually get nothing. So this is NR, no reaction, no reaction. However, if you do this reaction, you do actually get a product. If you perform this reaction, you do get a product, and that's puzzling. So look how it would look like. This is my leaving group. This is my lone pairs. And then we're going to talk in detail about what happens to those adjustments here, like with the OH not found, but look how it would look like. So here's your new product. Maybe I should just remove these. So here's your replacement. Of course, you have Br out. The question is, how come you get a reaction for this, but you do not get a reaction for the top one? And the reason why is because there are two mechanisms for nucleophilic substitution, and they are in competition with each other. So what you have is you actually have in substitution reactions, two different mechanisms. We call them SN1 and SN2. So in substitution, let me raise this up. You have either SN1 or SN2, and they are in competition. And your task is to discern based on several factors that we will study. So come with a clear mind, because there's going to be a bit of information given to you. But then afterward, after you learn the concept very, again, in a satisfactory level, you will actually very easily be able to tell which one is SN1, which one is SN2, and correspondingly draw the correct product. But they're all in competition. And then we will also learn when we get to chapter 8, which is elimination, that they are also in competition. They can be in competition with elimination reactions. So I'm letting you know from now that they can be in competition with elimination reactions. So that's it for now. Digest that, because when you come back in the next video, we will go into the SN2 reaction, probably the more important one in terms of the substitution reactions, and then again go over those factors in details.